Swayam Prabha. Digital India. Educated India.
Hi, so welcome back. So far we've been we've talked about turbulence, right? Where we've looked at the round jet, right? And we looked at similarity of certain variables, right? Then we've looked at mean velocities, etc., so far, right? And then we've also looked at the governing equations and how, if you apply them to a turbulent flow, the form they can take on, right? And essentially the governing equations, well, I mean, I guess they take on a rather formidable form where things like if you bring in the definition of turbulence, which we did as a mean component and a fluctuating component, then what we end up with when we incorporate that definition of the velocity into the governing equations is we come up with the Reynolds stresses. And these, of course, they again present you with a formidable challenge of having to solve them. But then ultimately that's what we need to do. We need to solve these equations, right? And the question is, how do we do that? Okay. So then, of course, I'm going to talk briefly about this because this can actually be another course completely. So and I'm not going to get into the details of solution procedures or solution methods, and but we have to talk about this because this is a very important, very important part of learning about turbulence. So I'm going to talk about that in that context, and I think you may have heard some of these names, so to speak, or solution methodologies. Okay, so let's talk about the one which is the most straightforward. It's actually most expensive, but it's also the most straightforward. Easy is not the word I would use, but given the all the methods, it's actually the most easy. The most simple approach. Let's put it that way. Okay, so which is essentially DNS. Okay, direct Navier-Stokes DNS. Okay, now so let me just write down. Okay, so DNS. Okay, so essentially you saw. Okay, so that is direct Navier-Stokes, okay, solution basically, direct Navier-Stokes. Okay, now here it's essentially it'll solve the Navier-Stokes equations, right, resolving all scales of motion. Okay. Right, with initial and boundary conditions, with initial and boundary conditions appropriate to the flow considered, right? Okay, and we're talking about simulation here. Okay, we're really talking about simulation. We're really talking about simulation. Okay, there is no modeling. Okay, we're not going to say that the mean velocity is equal to so much of the mean velocity is related to the free stream velocity in this fashion, nothing. Okay, like we did for the when we did that for the round free jet, right? So here we're just basically going to simulate, calculate each term, right? So that single simulation, it produces a single realization of the flow. It produces so essentially, the turbulent flow, I mean, there's so in, say for example, you study the flow for about, say, 1 minute, right? But there are, compare that to that of a flow which is laminar. Okay. Now, in this 1 minute, however, for a turbulent flow, you are going to see different scales of motion, different ways energy is being transferred, different sizes of eddies, and how and their random motion, etc., etc. So when I simulate, can I predict all of those, right? Or do I predict all of those? So the point is that when I do this, right now, so it has to be an unsteady analysis, obviously, right? And then it has to account for just all scales of motion, like I said, and the different physical processes that is going on. So a single simulation will actually produce a single realization of the flow, and there is actually, again, I repeat myself, there is no modeling, right? So as you can understand, this will involve tremendous amount of calculations because there are too many variables that you need to calculate, right? So this was actually not possible. I mean, is it going to be possible by hand? So it's only in around the 70s when powerful computers came along, then a calculation of this nature began to take shape. Okay, so so it's around the 1970s, right, that that this started taking shape, and so let's just say it came into sort of prominence or something. How do I write that? Yeah, maybe that, prominence, right? And due to the advent of prominence, due to advent of powerful computers, okay, and still it is really applicable low to moderate Reynolds number. That's important. So DNS, okay. All right, so let us see how we're going to go about, how best I can sort of explain, some of these things. Okay. All right. So now, so first itself, we're going to say that this is we're going to talk about homogeneous turbulence, right? Again, this is about okay. Now, what do we do here? So, when we started out, right, and we said we defined the velocity, right, as a fluctuating component and a mean velocity, isn't it? We did that. Now what we're going to do? We're going to kind of do something like that, except that we're going to say that there's really no mean here. Okay, everything is very random and very unsteady, and we're going to take all of those and try and solve them. Okay, it kind of amounts to that. So basically, we're going to say the velocity Okay. Okay, the velocity at space in a given instant of time, it consists of several modes of motion. Okay, and we represent that by a Fourier series, a 3D finite Fourier series, right? So we basically say that now I'm going to explain all of this. Okay, so bear with me. Something like called k e to the power okay. Okay, so we represent, so what we're doing here is we are essentially representing um, 3D finite right. So it's like, so essentially I have nothing, there is no like mean flow and a fluctuating part, pretty much everything is consistent. So we are just saying that the flow at each location and time is is a function of several, you know, well, is a combination, right, of several of these functions. I mean, you could say polynomials for that matter, right? That's what it will boil down to. So I'm going to just add up, sum up, you know, these different motions, and that's what will be the you know, complete velocity at that location and time, right? So it's just that what we see, for example, in nature, when I see a turbulent flow, right, what I see is I'm going to sort of break that down and say these are all individual motions, individual independent motions, right, which I am adding up to each other, and I see that big full form. So what I see, however, in nature is that the final form, so I'm almost like going back in you know, time, right, where I'm sort of breaking that down into those individual motions, right? Some may be big, some may be small. So that's why, you know, different scales of motion and how their movement, etc. So I do that and I add all of them up, and they should add up to the final flow that I see, right? So therefore, this is a Fourier series with which we do that. So that's the definition of the velocity that we are looking at right now. Okay, all right. So then, where here, let me just say here these, right? Now, right, are Fourier modes, right? This k, the k that you see here, right, over which this is summed up, this k, okay, well, E, okay, is actually equal to this, right, which is equal to this, right, and this is nothing but direction. Okay, what is k then? However, what the hell is k, right? So wave number vector, right, is the wave number vector. This is equal to okay, I think I should write this also here. Okay. So essentially, right, so that's what we are looking at. Okay. So this is how we are going to represent a velocity. Okay. Let me sort of do that a little bit, and then we can talk about it a little more in detail. Okay. Now, right, that is in Cartesian space, right. So now we're basically talking about the wave number space, right, and this is a Cartesian space, right. So this n, so this is then for equal to right. Okay. Then you see x, right, is equal to okay. Is that fine? I think why don't I write it like this? Okay. Then, well, actually, this also I should write as, say, this. Or no, should I write it like that? Yeah. Okay. Correct. Right? These are the unit vectors basically. Right? So then, right. So k, the dot product of k and x, I can write that as k naught E1 x1, right, and the dot product of n1 and n1, right, plus k naught E2 x2 okay. So this of course is 0, cos 0 is 1, so then this turns out to be E naught x1 or E2 x2 plus E3 x3, okay, right. So then e to the power I k dot x is equal to e to the power I k naught so k dot x is equal to k naught E1 x1 right. Then, well, as you now the thing is that e to the power, this is something I think, this is math I hope you can remember, I'm sure you know these, k naught, okay. If I do this, right, now this is equal to cos k naught E1 x1 plus I sine k naught E1 x1. Okay, so we can write that, right? So then, so similarly, you see where I'm going from here, right? So then, e to the power I k naught e2 x2 is equal to cos of k naught e2 x2 plus I sine k naught e2 x2, right? Let me write this also down so that, right, k naught e3 x3 plus I sine k naught e3 x3. You see, right? So the function, the relationship rather, was this, right? I sum this up. I really sum this up. So this is so this so e to the power I k x, right? So e to the power I k x is actually equal to this, right? So it's a sum of this, right? So as you can see that this is like, these are periodic functions, isn't it? So what we're saying here is, so e to the power I k x, so therefore this is, you just sum this up, right? So if you sum these up, okay, so if you sum this up, and that is going to be this, so e to the power, so this one, right? So essentially you could say that, so I'm going to, you know, just be a little brave and do this here, okay? So say this one is e to the power, this is first one, okay? Let's just say this one. So say cos and, you know, something like that. So let's just say it is something like that, okay? So the next one, okay, let's just say the 2, okay? Maybe something like that, right? And okay, right? Now you add all the three, right? You see the picture developing? You add all the three. What do I mean by that, right? What do I mean by that? So this, so these, you know, these axes are essentially x, right? And this is your function, you know, this whole function. So this is your x, right? This is your x. And these are your functions, right? So when I say add these up, how will you add these up? So you could take any location, right? So then this is your component here, this is a component, this is a component. And you put all these three, or you add this up, you know. So that is going to give you the amplitude. So this is almost like, if you see here, this is like the amplitude of the function, this one, right? It's almost this one. So amplitude of that into this, right? These are the Fourier modes, right? Okay, so so this is what we are actually sort of, this is what it is doing, right? Now to calculate all of these, as you can see, is going to get very tedious, you know. So that's where the problem is. Okay, so on and so forth. So now what is k naught? K naught is the lowest wave number. Okay, I'm going to just write that here. Okay, so then, so this is just to give you an idea. So k naught, where k naught actually lowest wave number. Okay. Yeah, right. So this is, as you can see, this is like a periodic function. Okay. As a matter of fact, I haven't exactly drawn these three as periodic functions, but anyway, you get the picture. So, but these, I could sort of do this a little more. So I could basically say that a nice little function like that. So another one, maybe something like that. Okay. Now, I think you'll see the difference between this and this. What is the, apart from the fact that this probably I didn't draw this correctly in terms of how I've written it here, this is not exactly a cost function or whatever. Let's just say, forget that for a while, but then this one is a periodic function. These are all periodic functions. So I will know the wave number, I know the frequency, I know the wavelength. So then I can calculate these values, right? I can actually calculate these values. And then however, when I put these three things together, then the thing is not going to look, as nicely as, then it will actually look, probably something of this sort. But when I will calculate it in this fashion, where at least, for each mode, so therefore, when I do this e to the power, at least one of these things, right? So here I know my parameters, I know my variables, and I should be able to calculate individual contributions due to this function. Okay, so that's the idea basically. Okay, so now, so essentially we are basically saying that this flow field that we are trying to represent, okay, this flow field that we are trying to represent, okay, turbulent flow field, okay, it's periodic, so I'm using these periodic functions sort of to represent, right. Now, where do I apply these? Where do I apply this? Well, we apply this to a domain, right, in physical space, such that right, where right L is large compared to the turbulent integral scale You understand? So essentially xi, what is this x that we are talking about? So we are talking, this is that x, this is the x, right? Now where is this x located? Because I have three different, I have x1, x2, x3, so I'm talking about x, y and z, right? Where are these located? So I define a domain such that, so I define a domain, right, this 1, 2, 3, which is, so each x is essentially less than this L. Now this L is large compared to the turbulent integral scale, because here we are, what is the integral scale that we are talking about? Well, we are summing it up, right, summing it up. So we are looking at all these x's within that domain. So that is, this essentially, this is a discrete method, right. So this is essentially integrating the function over this domain. So that domain is L, where L is large, so L is large compared, so where I integrate, right, that scale is well within this L, let's put it that way, okay. So K naught this L, okay. So K naught is the lowest wave number, right. So 2 pi by L, right, you understand. So so L is very large compared to the integral scale, and K naught is the lowest wave number, because this essentially means that I have, the wave which is going completely covering this L, right. So that's the wave number that we are talking about, okay. All right, now, okay, now so basically what are we saying? So we have a physical space, right? I consider a space, yeah, so let me draw that actually, why not? So let me draw the space. What's the best way to draw this? Okay. Let me draw this space here, okay. Okay. Okay, so let's just say this is cubic space, right? Okay. See where I'm going with this? So you have essentially let's just say that is C, right? This is your X and this is your Y, right? So you have these lines. So let's just say this is, so let's just say this one is, say, okay, so this length, okay, okay, so this is, say, x1, okay, then this is equal to x2 and this is equal to x3, right? So what are we talking about? This. That is x3, this is x2 and this is x1. Okay, and this x1, x2, x3 are much less than this L. Okay. So this is the domain that I am looking at. This is so so essentially we said, when we basically said that this is my 3D Fourier. So I'm going to look at homogeneous turbulence. How am I going to say? So I'm going to say that the velocity at some x and t. So which x and t? It lies within this domain, within this square, within this cube in the Cartesian coordinate system. So this is my domain, right? This is the domain of turbulence, let's put it that way, right? In this I have, so where is this x? So this x is x1, x2, x3 at some instant of time. So this x1, x2, x3 is essentially within this cube, right? And the maximum of that is basically, and these x's are much, these sizes of the lengths of the sides are much less than this L, right, which is very large compared to the integral scale L11. So where we, the way we integrate, so all of these, right, is much smaller than this L. So therefore, if I take the largest length of L, which is L, so I get the lowest wave number, which is Q naught, K naught, okay. Now, so essentially what we are saying is that in that cube, right, you have these various waves, right, all these modes or waves, right. So these are all different waves. Now, how I define those waves with what amplitude is the question. So we'll get to that, right? Or that is what we defined using something like that, right? So we defined it like this. So these are the Fourier modes, right? And then we said that it boils down to something like this. Essentially, we are saying that you add up all these different modes, right? And then, right, so I said, you know, each of these can be nice and periodic, and you put all of these things together, right? So now where do you put all these things? Where do these things exist? Again, in this cube, right? They exist in this cube. Now, how many of those are we going to consider? I mean, obviously, I mean, there's no way to tell that how many will be sufficient, I guess. I mean, what's the best way to answer that question? I mean, how many waves are you going to consider to properly represent the turbulence which exists in this domain, right? That's the question to ask. So, in DNS, okay, n3 number of n cube, right, n. So essentially, when I say this simulation is expensive, that's where we are getting to. Like now, because why is it expensive? Because if the more number of modes of more and more modes of motions that you look at, you know, it's going to take more and more time. You know, so it's only how much is possible is what we should be able to do. So anyway, so in DNS, right, n wave numbers, so NQ wave numbers are represented, right? So n of course is even, right? So n is even, right? So it obviously that determines the size of the in your simulation, right? Obviously. And obviously, that will also determine the RE. Hence, also determines the RE which can be achieved. Hence, we said that it is low to in the moderate Reynolds numbers, because that would mean, because you know that the higher the Reynolds number, we are in the large scale motion, larger eddy range, right? We've learned that so far now. It's interesting. Okay, so right. So now let's learn a little bit more about that. So then, so typically. N is rich in powers of 2. Okay, for example, 128, 198, etc. Right? So Ni that, okay, K max is, right, which is equal to pi n by L. Okay, so you understand what we're trying to do here. So we actually, are looking to represent. We are not. We are actually representing the velocity directly in the which will represent. We are representing the velocity in a turbulent flow field, in terms of waves which might exist there, right? In terms of fluctuations or waves. Now, how do I how do I know what kind of waves are there? How many are there? Well, that's what we're discussing. Right. So how many are there? Where are they? How are they? Moving. So that is why those are the questions that I need to answer. So this is the representation of the the velocity, right? And we see that it is represented as a as a Fourier series. Essentially, there are several modes of movement, and we put them together. Number of these waves, we put them together, and once I do that, I get a representation of the velocity. Where do I do that? In which so this is the domain, right? So it's a cubic space, and how many of those do I take? Well, it's n n cubes. That many I take, and that can, if I do a solution based on those, I seem to get accurate results, right? That's why DNS is so popular. Okay. However, it's a lot of calculation, so it is very expensive, right? But it's straightforward also, as you can see, right? So this is this whole I have a space in which I have distributed all sorts of waves. So this is kind of a spectral representation, right, of the velocity field in a turbulent flow, and this is essentially this is a so when I do that, so this right, this is spectral representation of the velocity, right, and this is actually similar to representing the velocity in a physical space, right, of n cube grid spacing, right. So this is similar to representing in physical space, right. So basically what I am saying is, we said the maximum length of the domain is L. So essentially you take a cube of L, right. So because that's the maximum cube that you will take, you do that, and you divide each side into n, and so I need not draw this again, I guess. So here, so essentially each cube, so then this one, so delta x. So delta x, for example, is nothing but L by x, L by n, right. Delta y is equal to L by n. Delta z is equal to L by n, right. So equal spacing. So I can say delta x is equal to L by n, okay, of uniform spacing. So delta x is equal to L by n, right, which is equal to pi by k max. So if you can visualize, just think about this, if you can visualize a space, right, which is sprayed, which is just sprayed with several waves, it's just all sorts of waves are moving around, right. So I'm just trying to visualize a spectral representation. I mean, this is like throwing jargons around, I don't like to do that. I'd like to visualize things and make it simple, and so that I understand. Okay, a physical space defined by the Cartesian coordinate system is something I understand, right? So this is something I understand. So this is a cube. It's a physical space, and that's it, right? I do that. Now, just think about another space where it's just strewn with several, just strewn with so many waves moving around, just moving around. So too many all sorts of, waves moving around. Okay. So we have, I'm just trying to visualize this in what way, you know, what do we mean by this? What is the space that we're talking about? What is this representation? Is it something like that, or what is it, right? Okay, maybe something like this. So all sorts of waves sort of moving around, right? Right? All sorts of waves are moving around. And what did we say? That u at some location x, right, t, right, is equal to, so we sum up several of these waves. On what basis? So we said this something about k, e to the power I kx, right? And what was that? This, right? This is what we represented right at the back, right in the beginning. This, right? So what are we saying then? Now, and the way we wrote that, we know that this one, for example, right? So it could be something like, you know, it's a cost function, cost of some function, right? So if I took that, right, and if I looked at this, so this would actually have several, you know, waves, you know, set of periodic waves, and you put them together, right? You break this up, right? And it's a full, you know, the space where you have lots of these moving around. Then you bunch them up, right? And it gives me a nice little, you know, information, a nice little wave, right? Which has its own properties. Now that wave represents my velocity at this location, right? And this location you could think of is essentially in a physical space. It looks something like a nice little cube here. And this is because we understand this space, right? We understand this space. So please try to understand that when I solve for those waves, this is not where I'm solving it. I'm solving that in that spectral space where I have just the waves. But when I put them together, you know, I represent that velocity at a location which you could actually place in a physical cube like this one. So what I'm trying to say is take some point here. So say some location, say this one, some location here, right? So this is x, y, z at some instant of time. So if I look at the velocity as this place, right? If I look at the velocity at this physical location, then the way I will need to calculate this, originally one way to do that initially was, what did we say? We said there's a mean velocity and a fluctuating bar. That's something we did in the episode. Now what we're doing is, we're saying this is a velocity, which is location of which is in this physical space. Now we go to the wave number spectral representation of this, right? So we go to the wave number space of this, right? And there we see that I have a space which has all these waves which are moving around. There I say that, you know, I'm going to bunch this up. So how many of these waves are you going to take? Which one are you going to take? So that you put together, right? That is given by this function here, right? So we put together, or we bunch up all these waves, and that gives me a representation of the velocity at this location. You get that? Okay, so that's, I think, pretty much, you know, what I would like to say. So quickly, I will just say two things, something about the discrete Fourier form and the first Fourier transform, and then we'll stop here. Okay, so I'm going to just say discrete Fourier transform, right? So this one, right, it gives a one-to-one mapping between the Fourier coefficients the Fourier modes and the velocities at n3 grid nodes. Okay. So, this one gives one-to-one mapping, right, between Fourier coefficients right. This is the Fourier modes that we are writing out, okay, and the velocities at so if I took that if I took the cube and I took delta x, delta y, delta z and made out a grid, then at each of these grid points I should be able to find a velocity, right. So, that velocity is actually given by this. So, that is why it is discrete. So, at each of these velocities is basically going to be given by the Fourier coefficient. If you can find that out, it gives you a one. So, that this is unique to the velocity at that location, right. So, that is a discrete Fourier form. The first Fourier transform FFT, right. What is that? Well, so essentially it is used to transform between wave number space and physical space on the order of n cube log n operations. Okay. So, you can see we are probably speeding it up. So, how are we doing that? Okay. So, this is used to transform between the wave number space and physical space. What do I mean by that? So, what I mean by that is, again, go and look at the Fourier modes, right, in the in that domain where you have only the waves, right, and connect that to the velocity at a particular location in the physical space. So, that is your physical space and this is the wave number space, right. So, you go to the wave number space, figure out, bunch up those different modes, right, put them together, and then that will give you the velocity in the physical space. So, essentially that, okay, that. So, but here how many operations do we do? N cube log n operations, right. Yeah. Now, you see a spectral method. So, this is basically fast Fourier transform. Now, a spectral method involves advancing the Fourier modes, right, in small time steps at delta t according to the Navier-Stokes equation in wave number space. So, essentially this involves, so spectral method, okay, okay. Now, this involves advancing the Fourier modes, right, in small time steps delta t, right, according to the Navier-Stokes equations, right, in wave number space. Right. We advance them by so that is the unsteady analysis. So, that is which is result essentially n to the power 6 operations, right, which essentially means this is a huge cost, it is expensive. So, that is why we think this is expensive. That's where the problem is, right? So what do we do? So what we do is the velocity field is transformed into physical space. The nonlinear terms are transformed into wave number space. Okay, so that's why you have n3 log n operations, and it's really called. So how do we avoid this? It's too expensive. How do you, so we are using, so with the word that I didn't use right at the beginning is the pseudo spectral method. So the spectral method is, you spray your, you go to a space where it is full of waves, and you pick out those waves, bunch them up, and that will represent the velocity of the flow field at a particular location, which is the location in the actual physical space. Now this is expensive. It's like into the POSIX operations. It's the spectral method. So now you say, but so how do can we sort of get around this? What we do is we just take the just the nonlinear terms, and those we represent using the Fourier modes. The rest of the velocity we leave in the physical space. Right. So we just take the nonlinear terms and we calculate those, we transform them to the wave number space, right, and leave the, so we just take the nonlinear terms to the wave number space, and the velocity field, the rest of the velocity is in the space, and then this n cube log n operations. Therefore, which is a quicker and less, right, and therefore it is called as a pseudospectral method. Okay, so I think I'll stop here. We'll do a little bit more on these, right? One more lecture, I think, and then we'll stop. Okay, so thank you.